Welcome to my YouTube channel. In this video, we are going to talk about PN Junction under equilibrium. So without any delay, let's start the video. Here in this presentation, we are going to talk about the behavior of the PN junction and the behavior of charge carriers like electrons and holes near the PN junction under equilibrium condition. Till this video, we have discussed about the behavior of electrons and holes when these P and N type semiconductors are kept separate. Now if we bring the P and N type semiconductor close to each other and if we try to develop a diode, then what will be the behavior of these electrons and holes in the junction of P and N type semiconductor? This is what we are going to cover in this presentation. We have to make an assumption here in this presentation that the doping level of P type semiconductor is much higher than the doping in N type semiconductor. That means holes in the P type semiconductor is much greater than the electrons in N type semiconductor. So the carrier concentration in these semiconductors, that is P and N type semiconductor, is given by P naught. Again, this naught is representing that the semiconductor is at equilibrium. Okay, so PP naught is given by, or PP naught is equal to Na, number of acceptor atoms in the semiconductor, and PP naught is nothing but the majority carriers in P plus semiconductor. Why we are putting a plus here? Because it is showing that P type semiconductor is very highly doped. Similarly, NP naught, that is the minority carrier in the P type semiconductor, or we can say electrons in P type semiconductor, is given by Ni square upon Na. This is derived from the mass action law. If you have not gone through the previous videos, then I would request you to please go through the previous videos to understand what is mass action law and how we can derive this equation. So remember, here P naught and N P naught is read as the number of holes in P type semiconductor, okay, and the number of electrons in P type semiconductor. So this P is representing the holes and this N is representing the electrons, and the subscript P is representing the P type semiconductor. Okay, so number of holes in P type semiconductor, which is the majority carriers, and number of electrons in the P type material, which is the minority carriers, is given by these two equations. So from the above equation, we can say PP naught is the number of holes in the P type material. We can say these are the majority carriers, okay, and NP naught is the number of electrons in P type material. These are minority carriers. Okay, let's continue. So how can we represent the energy band and the Fermi energy level in case of P plus type semiconductors? For that, we can draw the energy band diagram. Here we have the EC, conduction band, EV, valence band, and EI, this is the energy band of pure semiconductor, which is at the center of EC and EV. But after doping, we have studied in the previous slides or previous lectures that the Fermi energy moves closer to the valence band in case of p-type semiconductor. Therefore, the Fermi energy level EFP has moved closer to EV in case of p plus type semiconductor. Now let us talk about n-type semiconductor. So here the electron concentration in n-type semiconductor can be given by Nn naught, which is equal to Nd. And here D is representing the number of donor atoms. So what we can denote from here, this Nn naught is the majority carriers or majority electrons in n-type semiconductor. Similarly, the minority carriers in n-type semiconductor can be given by Pn naught, that is equal to Ni square upon Nd. So Nn naught and Pn naught. Okay, so here the subscript N is denoting the n-type semiconductor. N is representing the electrons and P is representing the holes. So from the above equations, we can say Nn naught is the number of electrons in n-type semiconductor and Pn naught is the number of holes in the n-type semiconductor. Here electrons are majority and holes are minority in case of n-type semiconductor. Now let us talk about the energy band diagram for n-type semiconductor. We have already discussed about the energy band diagram of n-type semiconductor in the previous videos, but just for a summary, here we have the EC, conduction band energy level, EV, valence band energy level, EI, intrinsic energy level, and EFN, that is the Fermi energy level. And we can see in case of n-type semiconductor, the Fermi energy level has moved upward closer to the conduction band. Now let us continue with the further more detailed discussion. So for P plus type semiconductor, the energy gap between EI and EFP is given by EI minus EFP. So the difference between the potential of EFP and EI, okay, is represented by EI minus EFP, which is equal to KT natural log of PP naught upon Ni. We have derived these equations in the previous lectures. Now to remove the natural log, we can take exponential function and we can represent PP naught, or the number of holes in p-type material, is given by Ni, the number of carriers in intrinsic semiconductor, multiplied by e to the power EI minus EFP divided by KT. Similarly, for the n-type semiconductor, we have EFN and EI, and we want to calculate the energy gap between EFN and EI, and that is given by EFN minus EI, that is equal to KT natural log of Nn naught, is the majority carrier, or we can say electrons in the n-type material, divided by Ni, the total charge in the intrinsic carrier or intrinsic semiconductor. Again, to remove the natural log, we can take the exponential function, and Nn naught is given by Ni multiplied by e to the power EFN minus EI divided by KT. So what we can observe from these two energy band diagram is that for P plus type materials, okay, since P plus type material is more doped compared to that of n type material, the EFP, okay, EFP has moved much closer to EV as compared to EFN with respect to EC. Okay, so here the gap in P plus type semiconductor, we can see this gap is much smaller compared to that of the gap between EC and EFN in case of N-type material. So this gap is very small for P plus type semiconductor and the gap is large for N-type semiconductor. So P-type semiconductor is highly doped. Therefore, this energy band gap of Fermi energy versus valence energy is much smaller compared to that of the gap in N-type material between EC and EFN. Now, if we combine these two materials, that is P plus type semiconductor with N-type semiconductor, we will get PN junction diode, and this is the nothing but PN junction diode. And now we are going to study about the behavior of charge carriers near the junction. So here we can divide the junction, and here we have the diagram of donors and acceptors. So the number of acceptors are more compared to that of number of donors in P plus N-type semiconductor. And what will happen to the junction and how the electrons and holes will move across the junctions. So we know that in case of P-type material, we have majority holes represented by here H, okay, and in case of N-type material we have electrons. Remember, the doping is much higher in case of P-type semiconductor, therefore I have densely packed the holes in the P-type material and lightly packed the electrons in the N-type material. So the electrons and holes which are very close to the junction will neutralize each other and they will form a junction barrier, and in the junction barrier we have ions present. So all the plus here has moved from the P-type semiconductor and crossed the junction, and similarly the minus representing here are the electrons which have diffused themselves with the holes near the junction, and this creates a barrier. Now beyond this, the holes cannot travel to the N-type semiconductor, and similarly the electrons cannot cross this barrier and reach to the P-type semiconductor. So let us define the boundaries of these junction and represent the energy band diagram. So we have EC, EV and EI, which is representing the conduction, valence and intrinsic semiconductors energy level. Similarly for N-type we have EC, EI and EV. Now there is one very interesting fact to remember, that we can see the energy in the EC is higher compared to the energy in EC of N-type, and the energy is gradually shifting and near the junction. So near the junction, if you see, we have a gradient for the energy levels, which is same for EI and EV. And what is very fascinating is that the Fermi energy is same, or it is almost constant throughout the junction also. So the Fermi energy remains constant even in the P-type region and N-type region, and it remains constant, or it actually balances itself and remains constant throughout the PN diode. Now what we can observe from here, so beyond this junction we have this P-type semiconductor, okay, and the rate of change of charges beyond the junction, okay, is almost constant. So dEI divided by dx, or the rate of change of EI with respect to distance dx, is 0. So there is no change of carrier concentration in P-type semiconductor beyond the junction. And this is the same for the charge carrier concentration in n-type semiconductor beyond the junction, and therefore this di upon dx, the rate of change of ei with respect to distance x is 0. So this says that the potential inside the p-type semiconductor beyond the junction and the potential in the n-type semiconductor beyond the junction is constant. Okay, but what about the energy in the junction area? And we can see there is a shift of energy or gradient of energy, and therefore the energy is not constant in this region, or we can say ei is varying, therefore dx upon dei is not 0. There is a shift in energy when we move in the junction. Now from this diagram, what are the things that we can observe? First thing that we can observe here is that hole concentration in p-type region is much greater than the electrons in n region. Therefore pp naught is much higher than pn naught. And due to abrupt change in the charge carriers, okay, near the junction, okay, the junction will have diffusion current. If you recall, diffusion current is generated whenever you have change in the concentration of charges in a particular region. So if there is a sudden change in the carrier concentration, there will be a diffusion current, and you don't need any external potential to make such a current to flow. So since because we were having very high concentration of hole here, okay, and less concentration of electron, suddenly there will be a diffusion current flowing from p to n-type semiconductor, and that is due to the change in concentration of the carriers in the junction. And this diffusion current will last for a very small time period. Due to diffusion current, the holes from p plus region will enter the n region, and similarly the electrons from n region will enter the p plus region. So holes will enter towards n region and electrons will enter towards p region, generating this barrier. So electric field is present only at the junction. So this junction is having some electric field because there is a potential gradient, and ei is varying with respect to distance in the junction. So ei is not constant, and we can see ei is varying in the junction, and this is called barrier potential, and we have to apply an external potential which should be greater than the barrier potential to make the current flow in case of PN diode. And what is the amount of external potential that we have to apply to make the currents flow? That will be given by Q multiplied by VBI. So VBI is nothing but the barrier potential or the junction potential. We have to apply an external potential, okay, via maybe a battery to make the electrons flow in the semiconductor or the PN junction diode, provided the battery should have a voltage greater than VBI. We call them threshold voltage or barrier voltage, and we have several names for this voltage. Now, the total positive ions in the n-type junction should be equal to the total negative charges in the p-type junction. What does that mean? So here the number of ions in the p-type region and the number of ions in the n-type region should be equal. But you can also observe that the penetration of holes in the n-type region is much higher compared to that of the penetration of electrons in the p-type region. This is due to because p-type is very highly doped, you can get enough holes in this region to diffuse with electrons, but the holes which are moving from the p-type region to the n-type region requires much more electrons. For that they have to travel much deeper in the n-type region, and therefore this gap or this junction's width is different in case of P plus type and n-type diode. So by equation we can say that Q multiplied by Nd multiplied by Xn should be equal to Q multiplied by Na multiplied by Xp, or Q and Q are same, so we can neglect these Q's and we will end up with Nd multiplied by Xn is equal to Na multiplied by Xp. What are Xn and Xp? So from this diagram we can see that P-type, this region is neutral in case of potential. Similarly, this region in N-type region is also neutral, but we have junction where we have ionized atoms in the junction which are completely ionized. Now, even in the region which is close to the junction of P plus type semiconductor and the actual junction, there will be a small gradient of electrons and holes, and similarly in this region we have small gradient of electrons and holes. This region represented by purple color are partially ionized. So we have three regions basically. One is neutral region, second is completely ionized region, and third is partially ionized regions. And the function or the gradient of these ionization is represented by this curve shown in purple line, and we can see this is exponential function, and here also we have exponential function. But again we have to keep an eye on the length of these functions. So this region is xp and this region is xn. So the number of the area up to which, or to the length up to which the holes have penetrated is given by xn, and the length up to which the electrons have penetrated is given by xp. And from the diagram we can see xn is greater than xp. And similarly, Q of Nd is much smaller than minus Q of Na. Why the minus is here? Because we have electrons in this region. Therefore, minus Q of Na is much higher than Q of Nd. If you take the area wise calculation, this area is always equal to this area. We will talk about these things in the upcoming slides. But anyway, what are the things that we can observe from this diagram? That there are three regions. First is neutral region, second is completely ionized region, thirdly there are partially ionized region, and the behavior of or the gradient of charge carriers near the partially ionized region are given by a kind of exponential function. And the depth of penetration of electron in the p-type region is much less than the depth of penetration of holes in the n-type region. So since Na is much greater than Ni, Xn is greater than Xp, because like I said, the holes will have to travel much larger distance in the n-type region to find electrons to pair up, whereas for the electrons which are coming from the n-type region will have to travel much lesser, because p-type is very highly dense. They will find enough holes to pair up, so the distance between xp and xn will be different, and we can say xn is greater than xp. So the p side is much heavily doped compared to that of n side. This is the reason why we have assumed p-type is greater than n-type, or the doping in p-type region is much greater than n-type region, because otherwise all these variables will become equal in nature. And With this, we can also understand if the doping is going to change in either p-type or n-type semiconductor, how this will affect the length of the total barrier, how it will affect the penetration of electrons and holes near the junction, and so on. Therefore, the depletion layer's length in p side or p plus side is much less than the n side region. With this, I would like to end the presentation because there are so many things to absorb. So I would request you to please go through this presentation, and if you have any doubts or suggestion, please share your doubts and suggestions in the comment section. If you have any comments or if you have any recommendations to modify the presentation, do share your recommendations. If you have not subscribed the channel, then I would request you to please subscribe the channel and share the video with your friends. Thank you and have a nice day.